Okay, you have got to see this. Every so often, a new technique comes along that is just so brilliant it completely changes the game. And today, we're looking at one that lets us create these unbelievably detailed simulations. I'm talking squishy objects, complex cloth, all running in real time. This is a huge deal.
And look, I know that sounds like a bold claim, but it is not an exaggeration. This breakthrough is finally unlocking the kind of rich, super responsive worlds in games and movies that, honestly, we've only been able to dream about until now. We're talking about a level of realism and interaction that just wasn't possible before.
So I want you to just look at this number for a second. 700,000. What in the world could that possibly mean? This isn't just some random big number. It is the absolute key to understanding the sheer scale and power of what we're about to unpack.
That's right, 700,000 vertices. You can think of them like individual knots in a massive, super complex fishing net. This technique can simulate every single one of them, all interacting with each other at speeds so fast you can actually play with it. It's astonishing.
Okay, so enough talk. Let's actually see what this leap in physics looks like. Because trust me, once you see the results, you're gonna get why everyone's so excited.
I mean, check this stuff out. We've got squishy balls covered in thousands of tiny, deforming bristles, all simulated perfectly. We've got layered cloth, where each piece slides over the other with just the right amount of friction, and let me tell you, that has been a grand challenge in computer graphics for decades. And it's so incredibly stable, you can literally grab and twist some elastic text, and the whole simulation doesn't just explode.
This kind of performance and stability is it's next level. So the question is, what's the secret sauce? How on earth is this possible? And here's the kicker, the most surprising part. There is no AI involved here, none. This is pure, old-fashioned human brilliance and some really clever problem solving.
So the whole method is actually built on this wonderfully simple and super effective idea. Let's break it down with an analogy that makes this whole thing incredibly easy to understand. It's called the manager and worker method.
Right, so just picture this in your head. The object you're trying to simulate is a gigantic net made of 700,000 interconnected rubber bands. Now, if you pull on just one little corner, the entire net stretches and deforms, right? Well, trying to calculate how every single one of those knots moves all at once is just way, way too slow, even for a crazy powerful computer.
So here's how they solve it. It's brilliant. The idea is, let's chop up that huge net into thousands of little tiny squares, and we give each little piece to a separate worker, think of it as a core on your graphics card, to solve all at the same time. This is super, super fast. But there's a problem. If each worker only knows about its own tiny piece, the net just falls apart. They have no idea what their neighbors are doing. And this is the solution, the aha moment. You hire a manager. The manager takes a blurry, big picture look at the whole net and tells the workers, hey guys, big picture, we're stretching to the right. The workers then adjust their little pieces to match that bigger goal, and bam, suddenly the whole thing works together perfectly. And hey, if you ever want to sound incredibly smart, the fancy scientific name for this whole hiring a manager trick is additive Schwartz preconditioning. But now you know, it's really just a super clever way to organize a massive problem so you can solve it at incredible speeds. Simple, right?
Now, as amazing as this is, it's not a silver bullet. It doesn't solve every single problem perfectly. Like any technique, it's got its limitations, so let's take a quick look at what those are.
So there are really two main things to keep in mind here. First, it's not quite as efficient when you're dealing with objects made of multiple materials that have really different stiffness levels. You know, the manager kind of struggles to coordinate when one part is like steel and the part right next to it is like jello. And second, while it is the absolute champion at around 700,000 vertices, it doesn't scale up quite as well into the millions. At that point, some other techniques might actually start to pull ahead.
But you know, beyond all the code and the algorithms, there's a bigger and I think more inspiring story here. This isn't just some technical achievement. It's really a testament to human ingenuity and the whole spirit of open science.
I just love this quote because it puts the spotlight exactly where it belongs. In an age where we all kind of default to thinking AI solves everything, this was created entirely by brilliant scientists by hand. It's such a powerful reminder of what the human mind is capable of, all on its own.
And what's even better is that the researchers, they just gave it all away. The paper, the source code, it's all online, totally free for anyone to use, to learn from, and to build on top of.
I mean, that's what moves science and technology forward for everybody. It's an incredibly generous thing to do.
But here's the really wild part. This paper was actually published way back in 2023, and it's been flying almost completely under the radar ever since. It's this hidden gem that's only now starting to get the attention and recognition it so clearly deserves. It just goes to show how important it is to seek out and celebrate this kind of incredible work.
And that really brings us to our final thought for today. As we continue to be just blown away by what artificial intelligence can do, breakthroughs like this one force us to ask a really important question. How do we make sure we continue to celebrate and support and champion the incredible power of pure human ingenuity? It's definitely something we're thinking about.